Welcome to this lecture series in group theory. In this lecture, we look at the notion of a morphism between two group actions. We'll see what that means, and let us recall some of the things that we need. So we have recalled and used orbit stabilizer theorem infinitely many times. It just says that if G is a group acting on a set X and little x belongs to capital X, then the cardinality of the orbit of X is same as the index of the stabilizer of the element X. I'm sure you know what this means. Let us also recall the definition of the coset action. If G is a group and H is a subgroup of G, then we can define an action of G on G mod H via this equation. And this is a legitimate action. We discussed properties of it and we saw some applications. All right, here are some problems. And now let us get to the material of this lecture. So before we get to the notion of morphism of two group actions, basically what is the point? The point is, just like in linear algebra, you have two vector spaces and you ask the question, when would you like to regard the two vector spaces as the same? They may be dressed differently, but all the vector spaceness may be exactly the same. So for instance, if you have a set X of cardinality n, then the set of all the maps from X to R is isomorphic to R to the n as a vector space. So it's just notationally different or artificially different, the two vector spaces. Similarly, if you have two groups, you can ask the question when they are really the same as groups, even though they may look different. And the notion of that, the corresponding notion of sameness is that of a group isomorphism. And similarly, if we have a group acting on a set X, when we would like to call this action, suppose G is a group acting on two sets, X and Y, when would we like to call the two actions the same, essentially the same in all the ways that matter? So that is why that is the query that we raise. It's an open-ended query, although it has a very precise answer. So suppose we have a group G acting on sets X and set X and a set Y. Let's say phi is the group homomorphism for the first action, and psi is the group homomorphism corresponding to the second action. The question is, when would you like to regard these two actions as the same? That is the question. And philosophically, what is going on is every element of G permutes things in X, so it induces a permutation which in the above notation is phi of G, and instead of writing phi of G, we will write phi sub G. Let me draw that again. So for an element G of G, we have a permutation of X, which we denote as phi sub G. We have a permutation of Y, which we denote as psi sub G. This is a Y. So an isomorphism between these two actions would be a bijection between X and Y, such that after you change these names, the permutation that you get here is same as you permute first and then change the name. So this think of F as changing the names, changing the dresses, and then whether you permute after changing the names or you first change the names and then permute. Sorry, I said the same thing twice. Whether you permute first and then change the names or you change the names and then permute, it should be the same thing. So an isomorphism between the two actions is a bijection such that the following diagram commutes. For all G in G, so what diagram commutes? We have this name changing map. We have the same name changing map again. All right, and here we have the permutation corresponding to G and the permutation corresponding to G. So this is the notion of an isomorphism. This is the name changing map, and whether you permute with the original names or you permute with the names changed by the same element of G, it's basically the same thing. So that's what this means. Formally, what we have written is psi g composed with f is f composed with phi g for all g in capital G. Right. So I hope this makes sense. And as usual, either in linear algebra or group theory or any other domain of mathematics, once we have the notion of an isomorphism, one may like to, or it is useful to relax the notion and get a notion of a homomorphism or just simply a morphism, as we call it. So here we are. Again, we have a group acting on sets x and y, and let's say phi and psi be the homomorphisms that determine the actions. Then a morphism from the first action to the second action is a map f from x to y such that this diagram, the diagram on the previous page basically, commutes for each g in the group. So we just drop the insistence that f is a bijection, that's all, just like we do in any other setting. So that's the notion of morphism. All right. Now we will look at the orbit stabilizer theorem in a different way, or you would say, how shall I say it? It's in a more structural way rather than just a cardinality statement. It is a more structural statement. What we are going to do is show a stronger version of what we have seen in the name of orbit stabilizer theorem. So fix an action of a group on a set X and fix an element in the set X. Then we get an action on the orbit of X. Right, and it's just the restriction of the original thing. So what is the action here? It's the same thing. G dot y is, well, let me not even write it. So this is a subset of X, but if you hit any element here by an element of G, you stay here. And the action of G on X restricts, as we call it, restricts to the action of G on the orbit of X. And this is a transitive action, right? All right. So let F be this map. G to orbit of X, defined as f of little g is G dot X. It's a legitimate map because this indeed lies in the orbit of X. So this is our map. This is not a group homomorphism or anything, of course. This is just this is a map of sets because this is not a group. This is just a set. So the thing is, by using set theoretic quotienting, this is exactly what we did when we were proving the cardinality version of orbit stabilizer theorem. So we saw there that this map F, if you find out the fibers of this map, it's just the cosets of the stabilizer of X. So let me not do that again, and here I will write the formal statement. The fibers, the non-empty fibers are, every fiber is non-empty. So the fibers of F are precisely the left cosets of stabilizer of X. So just do this as an exercise if you don't see this immediately. So basically, F factors through this thing to give a map F bar which is bijective. Right? That's not hard to see. And here is our claim. So we claim that. The action of G on G mod stabilizer of X, and this is the coset action. Here the action is the coset action, is isomorphic to the action of G on orbit of X. And the isomorphism is, in fact, F bar is an isomorphism. f bar from G mod stabilizer to orbit X is an isomorphism. So just give me a second. Here, I did not highlight this. I just want to highlight this. Right. So we will show basically that f bar is an isomorphism, and let me do that on a separate page. So all we need to check is, we need to check that for little g in capital G, this diagram, G mod stabilizer of X to orbit of X, G mod stabilizer of X, orbit of X. So what is this vertical map? The permutation induced by little g, what is that? That just takes X, stabilizer of X to, oh sorry, I shouldn't use X. Let me say maybe H. So the coset corresponding to H. This goes to GH, stabilizer of X. What is wrong with it? Oops, what's going on? Why can't I delete this? Strange. This goes to GH, stabilizer of X. And on the right hand side, it takes, well, Y to G dot Y. So this dot refers to the abstract action that we started with. All right, so we need to check that this commutes, yeah. So we need to check that for all G in G, the following diagram commutes. Or the above, basically this diagram commutes. So how do we check that? Basically, we start with a left coset of stabilizer. That, what does that map to? That maps to under f bar. What does that map to? That's the same as f of h, where recall what is f. F is that guy. So you start with h here, it becomes h stabilizer of x. That maps to f bar of whatever, but that is equal to f of h, because this diagram commutes. So f of h, and what is f of h? F of h is h dot x. All right. What does h dot x become under this pink map? It just simply becomes g dot h dot x, which is gh dot x. Okay. What about this guy under this map, orange map? It becomes gh stabilizer of x. And what does this become under f bar? It's the same as f of gh, which is gh dot x. And since these two things are equal, of course, they are the same things, we deduce that the diagram indeed commutes, and hence f bar is an isomorphism because it is a bijection. So f bar is a bijection. Hence f bar is an isomorphism between the left coset action, or rather the coset action as we call it, of G on this guy to this guy. So in terms of the coset action, we can state the orbit stabilizer theorem as the coset action of this on the what do you call it? The set of left cosets of the stabilizer is same as the action restricted to the orbit of x. And hence, in particular, these two things have the same cardinality because we already have a bijection between them. So this is a stronger statement than what we have been calling the orbit stabilizer theorem. All right, so that's that. I think that's that. Yeah. So that's all for this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.